All right, we will get started now. Oh, there we go. Okay, so today we're going to finish chapter 17. This is the last section that we're covering. And then we'll begin chapter 18. I think we'll have time at the end to do some Gen Chem 1 review as well. We may not, but just looking ahead, we should finish chapter 18 Friday. You'll notice that the PowerPoint is really short. It's like 28 pages. Or 28 slides. That's because we're nearing the end of the term, and now we're really focusing on the very key, most important pieces of each chapter. So previous chapters, there are like key, really important learning goals, and then there are some more details that we cover in our class. You might see in a practice problem or on one achieve homework problem, but they're not like the main focus of the chapter. So for 18 and 19 and just a tiny bit of 20, we're focusing on just the like key parts, but we definitely want Gen Chem 2 students to understand. So we'll finish 18 Friday. We will have a combined 19 and 20 chapter. It's also going to be pretty short. We'll have at least one full day of review, maybe 2 full days of review, depending on how long we take on the next chapter. So that's kind of just looking ahead, moving forward. So let's get into chapter 17. This last section, well, we talked about KSP. Remember that KSP, the solubility product constant, is a measure of a compound solubility. We calculated it with this question. We take the concentration of the ions that are generated in solution, multiply them together, and we get that KSP. So higher KSP would be more soluble, lower KSP is less soluble. But just like when we compared K and Q in the past, K is at equilibrium, Q is not at equilibrium. So we're going to talk about what it means for a solid to have a Q value higher or lower than its KSP. So KSP, K at equilibrium, Q not at equilibrium. That's all we need for those two blanks there. So if Q is less than K, that means that there are fewer ions in solution than there would be at equilibrium. If Q is equal to K, this means the solution is saturated. There is as much solid as there would be present at equilibrium, and any more solid added is just going to it's going to remain a solid. If Q, this should be greater than, this last one here, if Q is greater than KSP, then the solution is past the point of saturation. There would be too many ions in solution, so a precipitate would form. So if Q is less than KSP, more ions can be dissolved. If Q is greater than any excess ions will precipitate so precipitate meaning they'll form a solid. The ions will come together and form a solid. Precipitating from solution is what that means. And they will precipitate until Q equals KSP, or in other words, the solution reaches equilibrium. The amount of ions present in solution is equal to, or will give you, the KSP value. So this next slide here shows some images to relate solubility equilibrium. We're looking at equilibrium between a solid and a liquid. So solution at equilibrium. This is a dynamic equilibrium, which applies to all the other equilibriums that we have learned about. which means that when this type of solution is at equilibrium, we have solid and we have ions. That doesn't mean that none of the ions form a solid and none of the solid dissolves to form ions. That's happening at the same time. So we have arrows showing the solid form the ions, arrows showing the ions form the solid. That's all happening at the same time. This is what we mean by dynamic. But the net amount of solid does not change and the net amount of ions do not change. So this is at equilibrium. The net amounts are not changing. We have a certain amount of solid, certain amount of liquid. Certain amount of aqueous ions. If Q is less than K, this means that the amount of ions in solution, so this is specifically for solids, Q is less than K is P. The amount of ions in solution is less than what would be at equilibrium. And we can see this, in the picture, there's only 2 ions here, and at equilibrium there's definitely more. So that means if Q is less than KSP, the solid is going to reduce in mass and become ions to reach equilibrium. And then if Q is greater than K, this means we have a lot of ions in equilibrium, or in the solution, a lot of ions in the solution. To reach equilibrium, the ions have to precipitate and form a solid. So let's work through the last slide here, this learning check. We're supposing that equal volumes of a solution of 0.0015 molar silver chlorate and 0.0015 molar sodium chloride are mixed. Determine whether or not silver chloride precipitates from solution. Okay, so they give us information about silver chlorate, sodium chloride, and then they're asking about silver chloride. So let's think about why that is. Silver chlorate, if we dissolve that into solution, will form silver ions and chlorate ions. And then sodium chloride, if that's dissolved in solution, we get sodium ions and chloride ions. The question is about silver chloride. So these two compounds that are being added, when they are added to solution and dissociate, they form these ions, and then now we're wondering if AgCl, silver and chlorine, are going to precipitate and come together to form that solid. That precipitate will form if the Q value for silver and chloride is greater than the KSP value. So we need to calculate the Q value for silver chloride. So Q is the concentration of each ion raised to the power of the coefficient. Every single coefficient, all of these reactions are 1, so no exponents here. Okay, so I'm going to give you a minute to think about how can we find the concentrations of these ions. I'll give you a hint. It's not as straightforward as you might think. So we have equal volumes of 0.0015 molar silver chlorate and that same volume of 0.0015 molar sodium chloride. The molarities that are provided are then going to decrease when the two volumes are combined. We're doubling the amount of volume, so the concentration decreases. So given that equal volumes of each solution are mixed, the concentrations are the initial concentration divided by 2, which is 7.5 times 10 to the negative 4 molar. So volume is increasing, then concentration decreases. Now, everything initially had a 0.0015 molar concentration, so now everything has a 7.5 times 10 to the negative 4 molar concentration. So we can calculate Q by multiplying those two values, or multiplying that value by itself, because the concentration of silver is 7.5 times 10 to the negative 4. Concentration of chloride is the same. So we've calculated Q here. The question was to determine if silver chloride precipitates. Well, silver chloride KSP at equilibrium, the product of the concentrations of silver chloride is 1.77 times 10 to the negative 10. The Q that we calculated is greater than K. So that means at this time, with these two solutions mixed, there are more ions in solution than there should be at equilibrium of silver chloride. So what does that mean?
Like precipitate will form.
Precipitate will form, yes. There are more ions in solution, so to reach equilibrium, solid must be formed. So AgCl, silver chloride, precipitates. Questions on this? Yeah. Yeah, so this is the concentration of the solution of silver chloride. This is the concentration of the solution of sodium chloride. And then it said equal volumes were combined. So the concentration of silver initially is 0.0015. Let's say there was in 1 liter solution, but then that was added to another liter. So the volume doubled, the concentration decreases by 2. Because the two solutions were combined. Yeah, the last one. Other questions? Oops. Okay, we're going to move on to chapter 18 now. So let me open up that PowerPoint. Okay, so chapter 18 is all about chemical thermodynamics. It has to do with energy, and we'll talk about a bunch of different terms this semester. We talked a little bit about energy last term in Gen Chem 1, and we're just going to build upon that now. So thermodynamics is the study of how heat and work are involved in chemical reactions, so going from reactants to products, and in physical changes, so going from gas to liquid, liquid to solid, vice versa. So these are the sections that we will cover in this PowerPoint. So we're first talking about entropy and spontaneity. So if a reaction is spontaneous or not, and then how entropy can be used to explain that. So, like I said, thermodynamics, the study of how heat and work are involved in chemical reactions and physical changes. Spontaneous reactions or spontaneous processes occur under indicated conditions. So sometimes the conditions are just room temperature, standard pressure. Sometimes it's with extra temperature, lower heat, or that can all change. But under indicated conditions, if a process is spontaneous, it's going to occur. It might occur fast, it might occur slow, but either way, it's going to occur. Non-spontaneous processes don't happen under indicated conditions. And we'll use these words, spontaneous and non-spontaneous. So for example, we'll come back to this one, but the first slide of the PowerPoint was a picture of logs burning in a fire. If you were to take logs, put them in a fire pit, and then just sit and wait, those logs are not going to burn. Under those those conditions, room temperature, whatever temperature it is outside, and atmospheric pressure, if you do nothing to those logs, they're just going to sit there. They might decompose eventually. For a bonfire to occur, for a fire to occur, extra heat has to be added. So that's a condition where that process will become spontaneous, but with that extra energy added. So with this example, our conditions are 25 degrees Celsius, about room temperature, 1 atmosphere, which is the average pressure of our atmosphere. Which of these two processes are spontaneous? Water freezing to form ice or ice melting to form water? Yeah, ice melting to form water. That will happen at room temperature. If you have a beaker of water and set it out in the room, no matter how long you wait, that is not going to become ice at 25 degrees Celsius and 1 atm. If you change the temperature, it could. If you change the pressure, it could. But under these conditions, that is a non-spontaneous process. Ice melting, that is spontaneous at these indicated conditions. Okay, we'll come back to spontaneous and not spontaneous. But we're going to talk about these laws of thermodynamics here. So the first law of thermodynamics says that the total energy of the universe is constant. Or in other words, energy cannot be created or destroyed, but it can be transformed from one form to another. So the example of ice melting to form water. The universe that we're describing here is the system and its surroundings. The system is the ice melting. The surroundings are the air around the ice or the beaker that it's in. That's the surroundings. So the surroundings of the ice, around the ice, is providing energy that's absorbed by the ice for it to melt. Energy is not being created by the ice. It's just being transformed from the surrounding to the ice in order for it to melt. The second law of thermodynamics says that spontaneous processes always result in an overall increase in entropy. We're going to define entropy on the next slide. Of the universe. So if the system is ice, the surrounding is air around the ice, the universe is the system and the surrounding, so the ice and the air around it. So universe total energy will never change, but the system and the surrounding energies can change. Okay. So entropy. How many of you have heard of entropy? Just a few. Okay. Okay, so entropy is a measure of the degree of disorder in a system. So disorder is what you would think. Something's disorderly, it's unorganized. There's a lot of things everywhere, different locations that things could be at. More ordered, everything's in its correct spot, it's not moving around. It's kind of what we mean by, it's a measure of disorder. So more disorder means higher entropy. I don't know if the second bullet point is cut off for you, but if it is, we'll fill it in either way. In other words, entropy describes, this is the more scientific explanation or scientific way to describe entropy. It's the number of possible microstates of a system. Microstates means, you can kind of think of it as different possible locations of particles in a system. The example that I used in my morning class was you all are sitting, in your seats. You're probably not going to get up and move. You might have slightly different locations if you're like lean to the right, lean to the left, kind of move your arm forward and backward. Yeah, so those are some different microstates. Imagine if we put like 100 kids in here. And they're not in seats, they're running around. There's a lot more microstates of the room because those kids can be at many different locations. That increases the disorder and that increases the number of possible microstates. So when we're talking about phase changes, certain phase changes increase entropy. We start at the solid. Solids, we often might think about as being like stationary, those molecules are not moving. But the molecules that make up this countertop and the floor and your seats and tables are all like vibrating really slow back and forth. So they do have some movement. But there's not a lot of movement in the molecules. There's not a lot of locations where those molecules can be compared to a liquid. So imagine if we like melted this metal, for example, and it's in a beaker, we can move it around. There's a lot more locations where these metal particles can exist in that beaker. That is a greater number of microstates, that is greater disorder, because there's lots more locations for those little particles to be. So going from solid to liquid increases entropy, or you would say it has a positive delta S, solid to liquid, because the final entropy would be greater than the start. And then vice versa, if you take a liquid and then make it a solid, the entropy decreases, so you have delta S less than 0. Okay, so that's liquid or solid to liquid. If you go from liquid to gas, you want to imagine much more possible, greater number of microstates, much more disorder. This is another increase in entropy going from liquid to gas. So imagine a bunch of kids running around, lots of microstates, lots of, like if you took a snapshot of the room, different locations where those kids will be. Liquid, you can think of like what we're doing right now. You're not moving around very much. You're staying generally in the same location. But so there is some entropy, some movement, some disorder, but not the same as having a bunch of kids running around. And then the solid, you can kind of think of like the chairs in the room. They're also moving even less than you. They're not going to get up and walk out of the room, but they have a little bit of movement as well. So this shows phase changes. This is actually a video in the book. You can watch the molecules. The molecules move around. There are other changes that can result in a positive or negative entropy. This list is all positive values for delta S, which indicates an increase in entropy. So positive delta S, you might see it represented that way, or delta S greater than 0. All of that means increase in entropy. So the first two we saw on the previous slide. Going from a solid to a liquid, we increase disorder, increase microstates, increase entropy. Solid to a gas, same thing. Liquid to a gas, same thing. That's what this first blank is. Increasing microstates, increasing entropy. The dissolution of a solid into aqueous solution. So taking like potassium hydroxide and dissolving it into potassium and hydroxide ions. So this is a solid, these are aqueous. Well, now instead of potassium hydroxide being a solid sitting in a beaker, you dissolve it in water. Now we've got ions floating around. The ion isn't a liquid, so this isn't a phase change. I guess it is a phase change, but it's not a solid to liquid phase change, it's solid to aqueous. So more locations where the potassium can be, more locations where the sodium or hydroxide could be. This is an increase in entropy. An increase in temperature within a phase. So we're not changing phase for this bullet point. We're saying phase isn't changing, but if you have a liquid sample and you heat up the liquid, that also increases entropy. So you might remember temperature is a measure of kinetic energy. Kinetic energy is the energy of movement. So if you increase temperature, you're increasing the kinetic energy or the movement of those molecules. That's absorbing that energy from increasing temperature. So more movement, more microstates, higher entropy. And then lastly, we have an increase in the number of gas particles. So this would be like, I have to remember, N2O, I think, gas, forms N2 gas plus O2 gas. I actually don't know if that's the right starting material, but we'll use this as an example. We've got 1 mole of gas forming 2 moles. There's more gas particles present in the sample. This would be higher entropy, more microstates. Questions so far? Okay, let's go to the next slide and I'll have you all work on this. Which of these processes have positive change in entropy? So entropy is increasing. Think about each of these and then which one has a positive delta S. I'll give you all like 2 minutes to think about it. So 11:31 we'll review together. Okay, first we have sodium chloride dissolving in water. Sodium chloride is a solid. If it dissolves in water, it becomes sodium aqueous and chloride aqueous. This is a dissolution process. Looking back on our previous slide, that's bullet point number 3. So this has a positive change in entropy. So positive delta S, we're increasing the movement of the particles, increasing microstates, number of possible microstates, increasing disorder, increasing entropy. So positive delta S. Next we have water in a beaker evaporating when left out. So water in the beaker, water is a liquid, and when it evaporates, it becomes a gas. So we're going from liquid to gas. This is a positive delta S. Next, we have solid and gas forming just a solid. This is iron becoming rust, reacting with O2. So we have a solid, stays where it's at, doesn't move a lot. We have gas floating around the room, around the atmosphere, and then those react together and form a solid. In this reaction, we are decreasing the number of microstates, we're decreasing the disorder. So this will have a negative delta S. We'll say we're doing solid gas to just solid. We're decreasing the number of gas particles, decreasing microstates, decreasing disorder, decreasing entropy. Okay, and then we have solid and aqueous, forming aqueous and gas. We're increasing gas particles, so this will have a positive delta S. Questions on any of these? Okay, we'll go to next section. So we're going to talk about more about these entropy changes. So putting values to all of these having positive and negative delta S, we'll actually be able to calculate it in this section. Okay, so we're going to start with this third law of thermodynamics, which says that the entropy of a pure, perfectly ordered crystalline substance at absolute zero is 0. So I'm going to talk about what absolute 0 is. Absolute 0 is described as temperature in Kelvin being 0. Remember that 0 Celsius, so the freezing point of water, is 273 Kelvin. So we're getting 273 units below the freezing point of water. This is actually impossible to achieve, as far as I know. It would require some major instrument to be able to reach absolute 0. I don't think it's possible, but you should Google it and let me know if I'm wrong. But either way, at absolute 0, there would be no thermal energy. To cause the particles in a solid to move. So if it's perfectly ordered and it's completely pure and there's no movement in those solid particles, then it has 0 entropy. There's no disorder. It's completely ordered. They're not moving at all. So as far as I know, this is impossible to achieve, but this law is useful for determining absolute values of entropy, which are on the next slide. So standard molar entropies, these are the entropies of a substance determined under standard thermodynamic conditions. So 298 Kelvin, this is room temp, 25 degrees Celsius. 1 atmosphere is standard atmospheric pressure. Typical units, not unites, are joules per mole Kelvin. So this is the entropy in energy units for 1 mole of a substance at a certain temperature, the temperature being 298 Kelvin. So for example, the standard molar entropy of water as a liquid is 70.7 joules per mole Kelvin. So these are known values. They've been calculated for a variety of substances. If you had a physical textbook, the end of the book would have tables with all of these standard molar entropies. Your ebook also has these tables. They're just not like at the end. But we can use standard molar entropies. So S with that degree symbol, the degree indicates we're at standard temperature and pressure. These can be used to calculate entropy changes for chemical and physical processes, not properties. Lots of typos on this slide. So if we have a chemical reaction or you have a phase change, you can use standard molar entropies to calculate the change in entropy for that process. We're going to write the equation down here. First, going to define 2 letters that are going to be used. M is going to be in the equation. This refers to the coefficients of products. And then N will be coefficients of reactants. So I'm just going to write the equation here and we'll use it in the learning check on the next slide. So the delta S, standard molar entropy change for a reaction, is the sum, so Greek letter capital S, capital sigma, of the coefficients times the standard molar entropy of the products. So you add all those together, and then you subtract the sum of the coefficients times the standard molar entropies of the reactants. And that will give you delta S. So this looks very similar to an equation that we had last term when we were talking about bond energies or bond dissociation energies. So you could calculate, last term what we did was calculate the change in energy or enthalpy of a reaction based on bond dissociation energies, adding them all up for the products, and then subtracting the sum of that for the reactants. This setup of the change in entropy, change in enthalpy, change in Gibbs free energy, the setup is always the same. We use standard values, in this case molar entropies, to calculate the change. So we will use this in the next learning check. We will predict the sign of delta S first for this following reaction, and then use the data provided to calculate the standard molar entropy change. This last product should be O2 with a subscript there. So based on this reaction, before looking even at the values, do you think delta S is positive or negative?
Positive.
Why positive?
That is producing more gas.
It's producing more gas. Yeah, we're going from a solid, not very disorderly, to a liquid and a gas. So certainly increasing entropy. So positive delta S, or we can say delta S is greater than 0. Those mean the same things. Entropy increases. Now let's use the equation from the previous slide. I'm not going to rewrite it as it was on the previous slide. I'm just going to directly add values in. So use equation from previous slide. Delta S of this reaction is equal to coefficient of product. We have 2 moles of mercury, and then we need to multiply that by the standard molar entropy of mercury. If you look at the table, we have mercury liquid, mercury gas. Those have 2 different standard molar entropies, and we'd expect that because gases usually have higher entropy or always have higher entropy than liquids. So you just need to make sure you're using the entropy value for the same phase. So mercury liquid, entropy value 75.9. And then we have 1 mole of O2 times its standard molar entropy, 205.2. And then we subtract 2 moles of mercury oxide times the standard molar entropy, 70.3. And my students told me the value in the 9 a.m., but I didn't write it down. Will someone calculate it? I think it's like 216.4. Thank you. I think that's what we got in the morning. 216.4 joules per Kelvin. We can calculate. We can cancel out the mole unit. We will multiply that for the coefficient. Okay, 216.4, that's greater than 0. It's a positive value, so that aligns with our prediction. Yes? Oh, this is a negative. So these are the molar entropies of the products, and then we subtract molar entropy of the reactants. So that's I should have room to write it in the line. Other questions on this? Okay, let's do the next slide as well. I will wait to change the slide because I see some of you are still writing. This question says to predict the sign of delta S, just like we did for this problem, and calculate the change in entropy when we have 72.85 grams of liquid mercury vaporized. So we are taking liquid mercury, vaporizing it, That means it's going through a phase change. This isn't a chemical reaction, it's a phase change, but we have a change in entropy for phase changes as well. All good? Okay. So we're taking liquid mercury and making gaseous mercury. So what do we think for delta S? Yeah, greater than 0. Yeah, positive. Yes. Okay, so we can calculate. We're going to have a few steps. We'll calculate first the molar change in entropy. The standard molar entropies, we'll use the information from the previous slide. This is for 1 mole of a substance. In this question, we have 72.85 grams, so we'll have to figure out how many moles that is. But first, calculating entropy, delta S is the standard molar entropy of mercury gas, the product minus the standard molar entropy of mercury liquid, the reactant. And then we're just using values from the previous slide. So 175.0 joules per mole Kelvin minus 75.9 joules per mole Kelvin. So delta S here is 99.1 joules per mole Kelvin. This is the change in entropy for 1 mole of mercury liquid becoming gas. We have 72.85 grams. So we need to figure out, for this amount of mercury, what is the change in entropy. So what do we do next? We need to determine the amount of moles that we have. Yeah, did you all say something different? No, okay, same thing. Yep, so we've got 72.85 grams. One mole is 200.59 grams. And then we can continue and multiply this again by our standard molar entropy value. So we convert grams to moles, and then we can multiply 99.1 joules per mole times Kelvin. And then this will give us delta S 36.0 joules per Kelvin. So we cancel out grams, cancel out moles, and we are left with joules per Kelvin. And so this will be our final answer. Questions for me? Okay, we won't do review today. We'll do more in the future. Thanks, everybody. Have a good Wednesday.
Have a nice day.
Thanks, you too.